This is an old favorite. This is the ground state, so-called, before, but now I'm going to call it the sixth field. The reason for that, of course, is that we will see other fields with different nodes in the center. This happens to have a six-edged node in the center of the structure, and there's a uniform number of 4 edges all the way around the structure of this field. The purple denotes the tags of the main stem directions. Of course, we see that the structure of this field is flat. There's no distortion at all. It can lie on a plane and can be infinite in extent if we want. Whereas the 6 field was completely flat, the 5 field, which has a 5-edged node in the center of the ground state in green, has a distinct curvature. The curvature of this field is -1 because the 5-edged node itself has that curvature. This is the 4 field. In contrast to the 5 field, which had only a slight curvature, the 4 field has a much stronger curvature. As you can see, it's it's more concave when we look at it like this. You'll notice that there's a uniform number of edges, 4 edges in this case, around the periphery, and that the structure itself sits flat on the fiberboard. This is the 3 field because it has a 3-edged node of curvature -3 at the very center of the ground state, which is in green. The number of edges along the periphery are the same in all of the 3 directions. The structure itself sits flat on the fiberboard, and the concavity of the 3 field is much stronger than the 4 field, which itself was stronger than the 5 field, which itself was stronger than the 6 field, which is flat. So these negative curvature fields are caused by having a node at the center which has curvature in itself, and so the field is more constrained than the 6 field, which is hexagonally uniform in extent. Each of these fields, the 3, 4, 5, and 6 fields, can be infinite in extent. I've only showed just a certain portion. I might mention that each of the negative curvature fields is relatively constrained. That is, you can make motion in the field structure, the ground state portion, but it doesn't really change the structure of the nodes here. This is the 7 field. In contrast to the negative curvature fields 3, 4, and 5, which are concave, this is convex, and the 7 field has a certain sort of flexibility in it. So I can select this edge and these 3 edges here, or I can select this edge and these 3 edges here. So the 7-edge node has a certain sort of flexibility to it, and of course you can see the convex aspect of the 7 field. This is the 8 field, and you can see immediately from this image that the field is much more convex than the 7 field was, and so here you can see the extreme convexity of this structure. Like the 7-edge field, the 8-edge field has a certain sort of flexibility to it, more extreme than the 7 field. And so this is very interesting because it looks like there are several states of selection in the 8 field. This is the 9 field. It has extreme convexity. Look at this. I mean, it's just so convolved. And this is about the 9 field is about as far as the curvature can go. So the 6 is a 0 curvature, 7 is +1, 8 is +2, and so 9 would be +3 curvature. This is the 5 field once again. What I'll do is I'll project a defect pair in this channel here so that it will collide with this 5 edge node in the center. I won't bore you with the details of launching and moving the defect, but the defect had moved up in this channel, and now the defect, the 7 in pink and the 5 in light blue, have collided with the 5 at the center of the 5 field. So now there are two defect possibilities. This defect, the original one, can go back the way it came, or this defect here, the 7 and the 5 here, could go down in this channel here. So let's say we select that event to happen. The net result would be that this 5-7 would move off this way, but it would leave the 5 here. And so in effect what happened is that the 5 at the center of the field has moved from here to here. So now if we do the same thing over and over again, eventually the 5 at the 5 edge node at the center of the field will move off in this direction. Now, supposing you don't want that to happen, how would you prevent the field from changing its center? That was the question that I asked myself, and I'll show the answer that I have in the next section. I've restored the 5 field to its original state by taking out the defect structure. And now the 5 edge node is in the center of the field. What I've done is I've found a way of embedding a torus into the 5 field, and that takes the shape here. This is a single hole torus. You see that the hole itself is quite small. It's a 3 hole, and the path between this side and the other side is smooth, so the torus is deeply embedded in the 5 field. And then there's a structure away from the toroidal hole, the toroidal hole and the torus itself, and I've colored in orange all of the portion here, and then put into green the ground state that would go away. So you see that there are 4 edges on either side of the periphery of the ground state, the 5 field. And so now this is the way that the node can be stabilized. One could imagine defects impinging on this 5 field position and being deflected by the torus, either in this direction or in this direction, or defects coming in this way and being deflected like that, or being deflected like this. At least this is my sense. My sense is that the toroidal structure, the torus structure that I've added to the 5 field, will have the effect of stabilizing the position. Now, why would you want to do this? Well, if you had, for example, an icosahedron with 12 5-edge nodes at its corners, then if you took 12 of these structures, you could stabilize the structure and orientation of that ball, and that might be something you'd want to do. If we take the 4 field, I'll show you once again that the structure is relatively flat in the periphery. That is to say, there are 4 edges, no, there are 5 edges in each of the 4 directions of this 4 field. This is in contrast to the state that the thing is in when we add the torus. Now you'll notice here that the torus is of an entirely different structure, and it's much more contorted. It's difficult to see in the knuffles, but there's a certain sort of in a cavity here, and the structure is somewhat unsymmetric. I mean, it's symmetric in general, but there's this torsion here on this side and torsion or whatever on this side here. You'll also notice that the structure is only slightly stressed. That is to say, the far field of this forefield has a slight distortion in it. We'll see other cases where it's much more distorted. So this is the forefield, and as I said, the structure is entirely different than the structure of the torus for the three field, and that's interesting. So there can be possibly many different structural states here and different degrees of embedment, which maybe they, if we embedded, well, I see, yes, actually here you see here's the field structure, the ground state structure, but the hole in this case, which is a three hole once again, is sort of higher. There's a piece here that, so this hole is higher above the ground state than it was in the 5 case. So this fact that it's higher may be the thing that's inducing the distortion in the structure. I don't know, but I mean, it's something one could experiment with by making other models. So here's the three field once again. You notice that there's a slight bit of, I don't know what, distortion. Maybe it's just the knupffeles themselves that are doing that. In any case, I've done the same thing. I've embedded a torus into the three field. You'll notice that this is a rather more unsymmetric structure. I mean, it's really agonized is the way to think of it. And you'll notice that there's a lot of distortion in the three field remote from where the three edge node would have been. So this is really the point of this 5-4-3 process of the negative curvatures. That is, the three field really has a distortion in it far away from where the torus is. But once again, the idea is that if you had this three field here for some reason and you really wanted to keep it, then the torus would seem to be able to act to deflect defects that would be bombarding the three edge node that would be at the center of the three field. So these are, what I've shown you, are uniform fields in the sense that on the periphery, in this case in the three different directions, there's the same number of edges. Is that true? 1, 2, 3, 4, 5, 2, 3, 4. Yeah, they are the same. So these are simple states. In the end, further on this video, I'll show you a more complex ways that the tori can be bound to ground states. As I showed before, the 7 field has a certain flexibility in it, and any one of the rotational states could be used. But there are clearly two different states. There's the state in which this edge is selected and these 4 are selected, or a rotational state here where this edge is selected and then these 4 edges are selected. So supposing we want to stabilize this particular conformation of the 7 field. This is the 7 field in a bit larger version. I tried using just one toroidal object to stabilize the 7 field, but it just didn't seem to work. Maybe I should look a bit more. But so what I did in the end was I introduced a 3 pipe over here, which is some distance from the 7 edge node, and another 3 pipe over here, again the same distance from the 7 edge node. at the center of the 7 field. And then I constructed this pink object here, connecting this pipe to this pipe. And that had the effect of making this toroidal hole right here. So the structure was not really stable yet. So then the same distance from the 7-edge node, I constructed a third pipe and then added the pink ball to that. And without this structure here, the state that I want, the selection of this edge here and these 4 edges here, wasn't stable. So I added this light blue structure here, which had the effect of stabilizing the selection of the particular rotational conformation. But you notice there's this state here, but there's an equivalent state using this face here that could be constructed. And so there are 2 minor states within this stabilization structure. But by putting in this blue pipe here, which is a 3-pipe, bent at one point, we've induced a second toroidal hole right here. So there's one toroidal hole here, and there's the second toroidal hole here. And so it's necessary to use a torus 2 to stabilize a 7 field. So far, I've not been able to use a torus 1 to stabilize a 7 field. I know I seem to be sort of gilding the lily by giving all these different cases. I'm sorry. But there really is a point to this. And that is, I showed you before that the 8 field has a much greater flexibility. And whereas the 7 seemed to have one rotational state that could be stabilized, then the 8 field seems to have 2 states that could be stabilized. And so I set about to try to do that. This is the 8 field. In order to stabilize this particular conformation in here, I constructed a 3-pipe at 1 node away from the 8-edge node on this side, and then a 3-pipe on this side. And then I connected those 2 by means of this pink structure. And this had the effect of stabilizing the conformation somewhat, but there was still some wiggle in the structure. So what I did was I went to the other side of the fabric for an anti-torus and found that I could make a construction like this that would stabilize the structure completely. So now if I have a toroidal hole on this side and a toroidal hole on this side, now the structure is stable. But one is a torus on this side and the other is an anti-torus or an anti-particle if you want. So as far as the two-ness is concerned, well then just by choosing a state like this where the pipe here is connected and through the pink structure to the pipe here, well you see this has the effect of taking this structure away from over here. And so if we move this pipe over here, then the structure would be stable. And so these are the 2 states, I think, of the conformational stability of the 8 field, like this. You see this difference. So, but in each case, you have to have a torus on either side of the ground state, the 8 field. And that's rather interesting. Some time ago, when I first started to think about how to embed the toroidal objects into the ground state and into a 6 field, I built this object in red. It is rather twisted. You can see here how it's twisted, and it has a it has a hole. This looks like a 6-hole here, and it's fully embedded. The path between the 6th field on this side and the 6th field on this side is shallow, shows deep embedment of this toroidal object into the 6th field. So I built out the structure to the point in red, to the point where it was uniform, and there were no more, so for example, no more deviant nodes. So for example, there are 2 5-edge nodes over here, there's a 5-edge node over here, and there's 7-edge nodes around the periphery here. But beyond this, in light blue, this is the 6th field. This is all uniform 6-edge nodes here, all around here. Well, the reason for the distortion is that this is not a simple field. The embedment of this torus in the ground state in the 6th field changes it, distorts it, and that's easy to see. Along this edge here there are 9 nodes. Along here there are 4. Along here there are 5. Along here there are 7. Along here there are 4. And along here there are 5. I'm saying 5. 6. Okay. So this ground state, the 6th field, is highly distorted. It's not simple. Let me show you this in a diagram. So this diagram explains the difference between simple and complex 6 fields. This is a rather poor diagram of the structure of a 6 field that has 4 edges in all 6 directions. The structure that I was showing you before, the embedment of that red torus into the light blue 6 field, has these characteristics. There are 9, 4, 5, 7, 4, 6 edges around the 6 field periphery. So this is highly distorted. So what I did next was really ingenious. Very proud of myself. I took all of the red structure out. I cut it out. And that gave me just the blue structure. So then I had the red structure free, and I went back and I rebuilt exactly the same structure, so that I got back what I had to begin with. When I took the blue 6 field here with the distribution of lengths, number of edges that I told you about before, and I backfilled the structure, maintaining the 6 spines of the structure, I came to this state here, which is actually more distorted than before, because the toroidal object absorbs or induces part of the distortion. So freestanding by itself, the field is like this. So, you know, in physics they talk about every particle having a field. Well, you know, this is as close as I've come to exactly that. So these interactions here are some other set of events. Whether the single toroidal object is an adequate basis for distorting the 6th field in this fashion or not, I don't know. Certainly this structure here is interesting. I don't quite know what to make of this, but it is interesting. So then I took the next adventuresome step. Instead of trying to embed a particular toroidal object in a field and then seeing what the 6th field was like, I said, well, what about if I took a 5 field? We've seen this simple 5 field where the ground state portion away from the 5-edge node is uniform. Well, here's a case of a 5-edge node, or at least a ground state that has 5 peripheral sections, as denoted by the 5 purple lines. The periphery is 2, in terms of edges, 2, 5, 6, 4, 5. And it's highly distorted. You see that. So So now the question is, what toroidal object will embed itself in this? Now, I've not done this yet, but isn't that interesting? Here we have a particular confluence of events in a 5 field, and with a particular distortion. And now the question is, what's the embeddable object? And at some point I'll understand how to do these things in a systematic fashion, but not right now. This is the same sort of diagram as for the 6 field. Here's a uniform 5 field with, in this case, 5 edges around the periphery. But here's the one I was just describing with 2, 5, 6, 4, 5 edges, which is highly distorted. This slide is intended to summarize this video on fields. The negative curvature 3, 4, and 5 fields use a torus 1 to stabilize each of the fields. The positive curvature fields, the ones that I've done, 7 and 8, seem to use a torus 2 to stabilize the field. I've done at least one complex 6 field, and it seems to use a torus 1 to stabilize. I've developed a complex 5 field, but not built the embedded structure yet. It should be possible to embed more than one field into a perhaps torus 2 or larger structure. I've not done that. There should be general rules for determining the relationship between the torus number and the number of fields that can be bound, as well as the curvature of each of those fields. That's something that lies in the future.